We want to determine the work done by the vector field big F of xy is 5x plus 2y, comma, x squared plus 5y. On a particle that follows that path, r of t is 2 cos t, 2 sine t, or 0 less equal t less equal 2 pi. So think about that path. What is r of t? What does that give us? Well, it's a circle of radius 2, and it is traversed in a counterclockwise fashion. So that will be helpful for us as we try to solve this problem. It starts here at 0, 0, and it goes to 0, 2, comes down like this and goes around. So here is our path C. So the integral of C of f dot dr is what equals work. So what is that going to be? The integral over C of f dot dr. The integral over C of f, 5x plus 2y, comma, x squared plus 5y dot dx dy will be our work. And then we write it in the form we're sort of used to seeing, namely the integral over C of 5x plus 2y dx plus x squared plus 5y dy. And then we can go ahead and solve this. So what I would like to do first is I would like to just go ahead and do it with parameterization. So what do we know here? We know x is 2 cosine t. So dx dt is negative 2 sine t. So then dx would be negative 2 sine t dt. Similarly, y is 2 sine t. So dy dt is 2 cos t. So dy then would be 2 cos t dt. So let's make all of our substitutions. We see what this form is trying to be. Let's go ahead and rewrite this in terms of integrals in t. So there's my substitutions. 5x becomes 5 times 2 cos t, plus 2y becomes 2 times 2 sine t, and dx becomes negative 2 sine t dt. X squared becomes 2 cosine t squared, plus 5y plus 5 times 2 sine t. dy is 2 cos t dt. So let's do some more algebra to simplify this. 5 times 2 cos t is 10 cos t. 2 times 2 sine t is 4 sine t. 2 cos t squared is 4 cos squared t. 5 times 2 sine t is 10 sine t. Now let's go ahead and distribute to finish our setup. And we get here, which we certainly could feed to technology and see what it gets, but I want you to notice something. I have integral from 0 to 2 pi of 20t cos t here, an integral from 0 to 2 pi of negative 20 sine t cos t there. So I can actually simplify this into a single integral, if you will, from 0 to 2 pi of this piece minus that piece of 8 cos cubed t minus 8 sine squared t dt. So let's go ahead and feed that to technology and see what we get. So notice how I have it written, 8 times cos t to the third power minus 8 times sine t to the second power. Check the syntax, make sure it looks good, and our result appears to be negative 8 pi. So after all of that, we get negative 8 pi. But remember, we wanted the work done by the vector field on a particle that traversed a circle of radius 2. So this is what we have. And no, the vector field is not conservative. If it were, the work would be 0. Because if you're on a closed curve on a conservative vector field, the fundamental theorem of line integrals tells me all I have to do is determine the potential function, evaluate at the endpoints, and subtract. Well, that's not what I have here. So work will be, in this case, the double integral over r of n sub x minus m sub y dA. And we sure hope we're going to get our answer that we had previously of negative 8 pi. Well, what is m? What is n? M is the first piece in the vector field. M is 5x plus 2y. So m sub y is 2. What is n? N is the second piece. N is x squared plus 5y. What is n sub x? N sub x is 2x. So my work will be, again, a simply connected, piecewise smooth curve. We integrate over the boundary to find the work that's done, or we do the double integral over the entire region to find the work that's done if it satisfies the conditions of Green's theorem. So the double integral over the region R of n sub x minus m sub y, 2x minus 2 dy dx. But then we need to be smart because we want to convert this to polar coordinates to make this work. We can see that r goes from 0 to 2. We can say that theta goes from 0 to 2 pi of what? Of 2x minus 2. Well, what is x in the world of polar coordinates? That's 2r cos theta minus 2. What is dy dx? dy dx is, of course, r dr d theta. Now, this integral can be done, but I want to just go ahead and feed that to technology to see what it gives us. So here we go. The integral from 0 to 2 pi, integral from 0 to 2 of 2r cos theta minus 2 of r dr d theta is indeed equal to negative 8 pi. So this shows us that whether we use the parametrization technique or Green's theorem, we get the same answer. Now, most of the time, if you can use Green's theorem, it's a good idea to use it.